Hi, this is lecture 3 of week 2 of CS 1030, and we're continuing to talk about moving between pseudocode and Scratch. So in this lecture, we want to look at solving a problem, which is summing up the numbers from 1 to 10. So what we want is the value that's 1 plus 2 plus 3, etc., all the way up to 10. And we don't want to solve this just by writing a chain of addition statements. We want to solve this using a loop. And the reason we don't want to just write out a bunch of additions is, first of all, if there were a million of them, that just wouldn't work at all. And second of all, that program would be hard to adapt to the new situation where the number of things we wanted to add changes. So we want to solve this problem using a loop. And the question is, how do we take this abstract specification of a problem, summing up the numbers from 1 to 10 or 1 to whatever, and turn it into a computer program? And so the first thing to do is try to think about what variables do we need to keep track of. And then what we do is we sort of write code around those variables to actually solve the problem. So the variables that we're going to need to accomplish this task are, we're going to need a variable that sums up the values we've added up so far. So that value we're going to call it sum, is going to start at 0, and it's going to end up at the correct answer when the program finishes. And then we need a separate variable that counts up from 1 to 10, because that's going to represent the value that we're going to keep adding into the sum. And so this process of taking an abstract problem specification and breaking it down into a collection of variables and a collection of program operations on those variables, this is really hard, right? This is the essence of computer programming. And we're not only going to spend most of this semester working on this, but we're going to spend, you're going to spend most of the next 4 years working on it. So there's no reason to think that this would be easy and natural for you. And so we're just going to need to do a lot of practice. We're going to need to look at a lot of examples of doing this. And then that's how you learn how to make it work. So let's look at how we translate that, this sort of insight that we need these two variables, and let's look at how we write pseudocode around it to solve this problem. So here we have a pseudocode program which is going to ask the user for a number limit, and it's going to add up the numbers from 1 to that limit and then print it out. And so that's a little bit more general of a problem than summing up numbers from 1 to 10, but it's not really any harder to solve. So we're going to work with this more general version. So what we do is we're going to first have some code that sets up the conditions under which the algorithm can operate. And then the algorithm is going to run to completion and our program will be finished. So let's look at the setup. So we prompt the user by displaying enter a number limit, and then we get limit. And so remember, the get construct in Scratch basically asks the user for a value and stores it into the specified variable. Here it's limit. So now that we have limit set, we're going to initialize a new variable called sum to 0. That's the variable that's going to keep the running total of our additions. And we started at 0 because we haven't added anything into it yet. We're going to initialize a count variable to 1. And the reason we initialize the count variable to 1 is because that's the first thing we're going to add in. And so once we're at this point in the program, after this set count to 1, now we've set up the conditions and our setup is done, and the program can just do its main logic. So the main logic is entirely in a single while loop. And what the while loop does is says while count is less than or equal to limit, so the condition is count is less than or equal to limit, increment sum by count, so sum equals sum plus count, and then increment count by 1, make count bigger by 1. And so once we've done that action, we check whether we've done it enough times, and we've done it enough times when it's not the case that count is less than or equal to limit. And it's important in this particular program that we use less than or equal instead of less than. If we use less than and the user had entered a limit of 10, then it would only add up the numbers 1 through 9, and that's just not what we said we wanted. So less than or equal makes sure that we add up the correct number of things. And after the while loop terminates, after it's executed its last repetition, we can display the sum and it should contain the correct value. And so one thing we should ask ourselves once we write an algorithm is, is there anything that can go wrong with it? Could the user enter anything that would make this program do something weird or bad? And it turns out there is a problem with it. So a problem is, what if the user entered a negative number like negative 77? What would the program actually do? And to see this, let's look at what the while loop would do. So if limit was negative 77, we would say while count, which starts off at 1, is less than or equal to minus 77. So 1 is less than or equal to minus 77 evaluates to false. It's not true. And so what happens in that case is the action part of the while loop never gets executed at all, and the sum of 0 gets displayed. And that might not have been what we wanted. So let's look at a way to make our program better so that it can detect this error condition and do something more sensible. So here are two ways to fix it. On the left-hand side, we're going to only check the limit value once. So we're going to get limit from the user. We're going to say if limit is less than 0, display a value to the user, display a message to the user, needed a positive number. And otherwise, then we're going to do the actual algorithm. And so if limit is less than 0, we're going to just display an error. If limit is greater than or equal to 0, we can proceed with the algorithm. And so that's probably a perfectly sensible thing to do. If the user does something that causes our computation to not make sense, we display an error message instead of actually trying to do a computation that doesn't make sense. And that's just very friendly. And this kind of process of anticipating things that can go wrong and actually detecting them and doing something friendly instead of making your program do something kind of crazy and wrong, this is really important. It's really not necessarily easy. And it's something that it's a skill that you'll use your entire career as a programmer. And so it's good to get started right now very early in your career. So another way we could fix the problem is to wrap the get in a loop. So let's look at how this works. So we're going to get a limit from the user, and while that limit is less than 0, we're going to display enter a positive, and then get a new value for a limit. So what this is going to do is keep asking the user for a value until they enter something that's not less than 0. Once it's not less than 0, then this while loop terminates, and we can execute the main logic of the code. And the main logic of the code here is shown in red, and it's the same on both sides of the slide. So again, error checking is important. It's something that we need to get used to doing when we write programs, and a failure to do it is one of the reasons that a lot of software sort of appears to sort of suck, for want of a better word. The software appears bad because it didn't give us a friendly error. It rather just went ahead and did something that didn't make any sense. Okay, so now that we're done with that topic, we're going to go look at repetition constructs in Scratch. So we're going to want to end up with a Scratch program that implements the same thing as our pseudocode here. So let's look at what Scratch gives us. So in the previous lecture segment for this week, we've already looked at one of the repetition constructs for Scratch, which is the repeat until. And the repeat until construct is parameterized by two things. There's this hexagonal hole where we can put any kind of a condition, and then there's this space in the middle where we can put any amount of Scratch code that we want. We can put the action part of the construct in the hole, or sorry, in this gap in the middle of the repetition construct. So Scratch doesn't have only this repetition construct. There's two more, and they're both easier. So first of all, it has a repeat construct, and the repeat construct isn't parameterized by a condition, but rather by a number of times to repeat. So if you put some number here like 10, then whatever actions you put inside of the repetition construct are going to get executed 10 times. So then at the bottom here, we have the final repetition construct in Scratch that doesn't take any kind of a number of repetitions or a condition. It just takes whatever action you put here and executes it forever, unless something sort of happens to break it out of the loop. And there's ways to do this in Scratch, or of course you could turn off your computer or something if you want to stop the forever loop. But left to itself, the forever loop is just going to keep executing the action until the end of time. So if you remember from our pseudocode, we had while count is less than or equal to limit. And the question is going to be, which of the repetition constructs in Scratch do we want to map that to? So as we saw in the previous lecture, it's pretty easy to map the while loop until the repeat until loop. All we need to do is flip the sense of the condition. And then we can get a loop that means the same thing in Scratch that it meant in the pseudocode. So let's look at how this all comes together. So here's a complete Scratch program on the right-hand part of the slide that solves the problem that we just solved in pseudocode. And the thing I'd like you to take away from this, and this is actually sort of something that's kind of cool, is that the Scratch code matches the pseudocode really well. Once you get past the sort of colors and the funny shapes of things, there's an almost exact match. So for example, where the pseudocode would prompt the user for something, Scratch does the same thing. And where the pseudocode would initialize a variable called sum to 0, the Scratch does something that looks extremely similar. And it turns out the only real differences here are the Scratch code needs a way to get started. This while green flag or when green flag is clicked is going to start the code. The pseudocode didn't need that, so we had to add that. The pseudocode doesn't exactly display things in quite the same way. It's going to put up a dialog that's up for 2 seconds that displays the final answer for 2 seconds. That's something we didn't need to do in a pseudocode. And then the only real other difference is the loop construct is different. We already talked about that. So again, we get a pretty straightforward translation from pseudocode to Scratch, and that's really good because what it means is if we can write down pseudocode that works, we can get Scratch that works pretty easily, pretty mechanically, and that's really nice. So what I'd like to do now is look at how we could have solved this same problem using the other kinds of loop constructs that Scratch provides. And let's look at how to do that using using the repeat a limit number of times construct. So here we're using the repeat construct to solve the problem. And so what we can do is we can repeat the limit number of times the same loop body that we had earlier. And the question is, does this work, or why does it work? Well, it works because this is going to execute the loop body or the loop action 10 times, and it's not going to have the same kind of condition as the other loop in Scratch, but it's going to have the same overall effect. And the reason that we would like to practice expressing the same computation in different ways is when you read code written by others, or when you write code, you often have choices, or the other people writing code had choices. There's often a lot of different ways to say the same thing when writing a computer program. And what we'd like to do is sort of get started learning how to recognize that things that look different are actually the same. And then also we'd like to practice in figuring out what's the right way to solve a problem. There's often a lot of different ways to say something in a computer program, but it's often the case that there's one sort of best way. And one of the things we'd like to teach you in the next over your 4 years here is how to actually make that make these choices in a way that's kind of pleasing and ends up with good code that other people you work with can actually sort of read and appreciate. So that solved the problem using the repeat loop. And another question we could ask is, can we solve the same problem using the forever loop? And this ends up getting a little bit awkward. We can, but it's not real natural. So we have a forever loop, and it's going to solve the it's going to execute the same loop body, but then it doesn't have a natural way to stop. So we're going to actually have to insert specific code into the forever loop to stop it. So once count is greater than limit, we're going to say the answer, say the sum, and then we're just going to terminate the whole program. So the stop all just terminates our program. So what we've done here is sort of built a while loop or built a repeat loop using the forever loop. And it's really not very pleasing or elegant. It's not the way I would have chosen to solve this. And I hope it's not the way you would choose to solve it, but it does at least work. It's just more complicated than it needs to be. And again, this is a very common pattern where there's multiple ways to solve a problem, and some of them are better and some of them are worse. And what we want is for all of us to get some practice in recognizing the good ones so we can write the good one the first time, so our code is sort of smaller and nicer and easier to understand. Okay, so to recap, we design an algorithm by first trying to write it down in pseudocode, and this is where the heavy lifting is done, at least ideally. This is where the heavy lifting is done because this is where we have to translate the abstract specification into pseudocode, and this is just fundamentally not really a very easy thing. It's hard, it takes a lot of practice. Secondly, we can translate the pseudocode into a real programming language, and this step shouldn't be as hard because hopefully there can be a more or less mechanical translation where we just replace pseudocode elements with elements of an actual programming language. So that's something that's really important that we looked at today. Another thing that we want to talk about, sort of emphasize, is this idea of finding the opposite of a condition. That's sort of useful in general. It's a generally useful skill that you'll have to do fairly often when writing computer programs. So we'd like to know some ways to do it. And if you remember from the previous lecture, we can either wrap the condition in a not, which reverses its sense, or we can go inside the condition and flip the individual elements. So that's important too. And the third thing I'd like to just sort of emphasize from this lecture, or from this material, is that there's different ways to express repetition in a computer language. Most computer languages provide more than one, so Scratch provides 3. And we want to start getting a sense for us when to use which of them to make our program sort of read in the most natural way possible. Thank you.